Let's take a look at elemental composition of pure substances. So our ultimate goal is going to be to look at the relationship between elemental composition by mass and the empirical formula for a pure substance. But we're going to start by just defining a pure substance and percent composition. For this, there's two pieces of essential knowledge. The first is that a pure substance has fixed proportions, and that because of that, we have the law of definite proportions, which states that the masses of the elements that make up pure substances is constant with regard to the total mass. So let's take a look. First, let's define pure substances. These are elements and compounds, and they have fixed compositions. And for elements, fixed compositions means that all the atoms in the sample are of the same element. For compounds, fixed compositions means that two or more atoms are bonded in a fixed ratio. So here, 1 red to 2 white, and that is the repeating fixed ratio. And I can see this in pretty much all compounds, this fixed ratio. Sodium chloride has a fixed ratio of 1 sodium to 1 chlorine. So we say that's a 1-to-1 ratio. Carbon dioxide has a ratio of 1 carbon for every 2 oxygens. And really, we're looking at the subscripts in the formula to give me that ratio. That's what those subscripts describe, 1 carbon to 2 oxygen. Now, if I know that they have a fixed ratio, then that means they also have a constant mass ratio. If I think about them in terms of mass, 22.99 atomic mass units for sodium, 35.45 atomic mass units for chlorine, these masses will never change because it's 1 sodium, 1 chlorine. So I can describe the ratio by mass as well. And I'm going to do this by taking the part that is sodium, comparing it to the total. It's actually going to give me a percent. I can do that for carbon dioxide as well and describe all of these things in terms of mass. And this is the idea of percent composition, the percent by mass of an element in a compound. And percent composition is useful because it can be used as evidence for the purity of a sample that I'm looking at. Because if I know what percent of an element I'm supposed to have in the sample, if I do an experiment where I'm measuring the amount that's of an element in a sample and compare it to the expected percent composition, I can see if it's pure or not. And if those percents don't match up, then I can try to figure out what the impurity is. You could also use it as a piece of evidence for identifying an unknown sample. And the equation is fairly straightforward. It's the mass of the atoms of a single element divided by the mass of all the atoms in the compound times 100. So let's take a look at an example. Let's do the percent composition of the elements in vanillin. Vanillin is C8H8O3. And it's the compound that is extracted from vanilla beans to give us the vanilla flavor. The first thing I want to do to find the percent composition is find out how much mass is coming from each individual atom. So we're going to take the atomic mass of each atom and multiply by the number of atoms that we have. So that's 8 carbons, 8 hydrogens, 3 oxygens. 8 times 12 for carbon, 8 times 1 for hydrogen, 3 times 16 for oxygen. These are my individual element masses. Now, the second thing I want to do is get the total for the entire formula. So this looks very similar to the way we normally get the molar mass of this compound. And I'm just going to add them up. So 152.144. And now all I'm going to do is apply that formula. Take the part that is carbon, divided by the total. Take the part that is hydrogen, divided by the total. And take the part that is oxygen and divide it by the total. This compound has a percent composition of 63.2% carbon, 5.3% hydrogen, and 31.5% oxygen.